Hi, and welcome to this next clip in this series of acid and alkali section for A-level chemistry. This is the seventh one in this series, and in the previous clip we looked at the pH changes of strong acids when we added a small amount of base to them. In this clip what we're going to do is do the same thing, but this time we are going to look at a weak acid. When we use a weak acid, we obviously now have the slightly more complicated situation whereby we have to incorporate the Ka into any of the pH calculations. And so when we add sodium hydroxide to ethanoic acid, we are going to create the sodium ethanoate salt, and we are also going to produce water, much in a very generic acid plus alkali gives a salt plus water style. But as we've just said, for a weak acid we have to know the Ka value or the pKa value for that weak acid, which then allows us, if we had started with a concentration of say 0.01 moles per litre, then we have the equation whereby H plus is now related to the Ka and the initial concentration of the acid by this equation, which we helped to derive in some of the previous clips, and this allows us to generate the H plus ion concentration for the ethanoic acid as it starts life. So the initial concentration of 0.1 molar solution will have a concentration of something in the region of 1.3 times 10 to the minus 3 molar, and that will give rise to a pH. Once you put that into the minus log base 10 equation, as usual, will give you something in the region of 2.88 to 2 decimal places. Now, if we say that the initial volume of the acid is 25 centimeters cubed, and we are going to add to this 10 centimeters cubed of sodium hydroxide, and to make life a little bit easier we'll make that a 0.1 molar solution as well. We need to calculate the number of moles of each of the substances, moles being the concentration multiplied by the volume we have divided by 1,000, and this will be consistent for both of the reagents that we're using. So for ethanoic acid, that will be 0.1 times 25 divided by 1,000, giving us a value of 0.0025. And likewise for the sodium hydroxide, we'll have a value of 0.1 times 10 this time, divided by 1,000, and this time giving us a number of moles of 0.001 moles. So slightly smaller number of moles. But these two are going to react with each other, and the sodium hydroxide is going to neutralize some of the ethanoic acid, leaving us with a moles of acid left after the reaction of 0.0025, subtract the 0.001. So much like we would do in an equilibrium type reaction where we use terms like 1 minus x, etc. And this would then leave us with a number of moles of 0.0015. So that would be for the concentration of the acid that is remaining. And in this situation, if it was a strong acid, we would then simply insert that into the pH minus log base 10 equation and generate ourselves a pH. However, because this is a weak acid, and we know that Ka in a weak acid is equal to H plus multiplied by the concentration of its conjugate base, so in this case that will be the ethanoate ion, divided by the concentration of the parent acid, so ethanoic acid in this case, we can now see that in the course of this reaction we have also generated some salt. So the salt being the ethanoate ion here. Now, because this ion has been generated, we see that these two terms are now not equal. If you remember in a previous clip, we looked at the situation whereby H plus was equal to the salt concentration, and therefore we could simplify that equation down to the H plus squared equation, the origin of the equation on the left there. So that was seen previously in an earlier clip. But now we have this reaction whereby we have actually generated some salt. And the salt we have generated is equal to, in this situation, equal to the number of moles of the sodium hydroxide that we used in the reaction. So the amount of product that we will generate of salt is equal to also here 0.001 moles. Now this complicates this equation slightly now, because we have to again rearrange this to generate H plus, and we do that by taking our equilibrium constant, and we now multiply by the parent acid concentration divided by the salt concentration. And what we're essentially doing here is looking at a ratio of the acid concentration and also the base concentration, the conjugate base concentration within our new system. And we have to be able to generate these values in this equation. Now, we know Ka, we were given that, you would be given this in a question, that would be 1.75 times 10 to the minus 5. And we need to now multiply by this ratio of acid divided by concentration of conjugate base. Now, we have already calculated the number of moles of acid, which is here on the left hand side, the 0.0015, and we have also calculated the number of moles of the salt, that being this 0.001 here. And we can use those two ratios directly. We don't have to convert them into concentrations, because ultimately if we were to convert into concentrations, the factors of 1,000 that we would need would cancel out, and subsequently the factors of the volumes would also cancel out. So it is possible to simplify it slightly and simply use a ratio of the moles when we have this situation whereby we have a 1-to-1 ratio. This then allows us to numerically calculate the answer to the H plus ion concentration, which gives us 2.63 times 10 to the minus 5 molar. This concentration of H plus then allows us to calculate a pH by placing into the usual pH minus log base 10 equation and giving us a final pH of 4.58. Now, some questions may be worded where they ask you to calculate a pH change, in which case you'd have to subtract the initial pH of 2.88 from this value to give that subsequent pH change. But here we'll just leave it with the pH of the final acid that we've got after we have reacted some of the sodium hydroxide. So just to recap that, because we're using a weak acid and we have this relationship between the three variables, H plus, conjugate base, parent acid, and also the Ka value, simply using H plus ion concentrations in a strong acid situation doesn't work for us. In this situation whereby we add some sodium hydroxide, a strong base, to a solution of a weak acid, we've ultimately created a buffer situation. And we will look at buffers in more detail in another couple of clips. But for now, this allows us to calculate pH changes of weak acids, and we've also done previously the pH change of strong acids as well. As I say, in the next couple of clips, we'll start to look at buffers, and we'll also look at choice of indicators to finish off this acid-alkali series. So thank you very much, and I will see you in the next one.